now we have Francesco Vuolo. He's going to present us a use case learning monitoring products for agriculture. I already saw a few questions, actually. Maybe later on you can answer related to
Thank you very
crops
much,
and agriculture. Yes, welcome. The floor is yours.
Thanks for the invitation and thanks to all the participants for listening. I will try to give you an introduction on some of the monitoring products that we use for agriculture, in particular bringing examples from a project and going a bit beyond the project context. A brief introduction about myself. I'm basically a scientist, so you will have the view of a scientist on deploying on big IT infrastructure. And I'm specialized in the use of optical data, so in particular Sentinel-2, Landsat-8. This is a bit my domain of application, looking at problems such as length over, length use, and classification, so a classic of remote sensing, but also going into more continuous variables retrieval. Question was about leaf area index. My presentation might be able to answer that question. And later in my work, also on making such processing operational so that they can be used and we can capitalize on the data, on the services that are there, in particular for precision farming or data-driven farming. I also tell you a little bit about the major milestones that I have gone through my career and how we got to this point. So I started working in this area many years ago already. And the first, I think, big achievement was in 2016 when Sentinel was just making the first rounds around the Earth. We were already able to provide in very short time services for providing atmospheric correction and the level 2A data. And in addition, products such as albedo, leaf area index, looking at agricultural lands in particular. So those were the precursors of what we know today as the diocese infrastructures. And we had a very strong focus on agriculture. We went into providing services for smoothing and gap filling data. We all know problems related to clouds and irregular data spacing. And the users, in our case, farmers, were asking for continuous data stream. Every day we want the data. We don't care about clouds. And we moved then in 2020 with the collection of a bit more advanced algorithm to look at vegetation, doing the monitoring of it, but also the management. And lately, we completed the Koala project, which will be the main topic of the presentation I'm going to deliver today, to implement, test, validate, consolidate a number of products and services that are today available for data-driven agriculture or satellite-based data-driven agriculture. So our projects have been funded by the European Commission with some national funding in the very early stage from I'm based in Austria, from the National Funding Agency for Space Activities. A little bit about the connections between my institution and the WEkEO. So we are, as I said, we are in Vienna. We are primarily an education center, university. We do research, but we also, and we applied research. So as I say, we also work a lot with farmers outside, and we try to develop in their direction to support them. We all know that Sentinel data are offer large volume of data. And many years ago, 2015, I think, we partnered with the EODC, which is the Earth Observation Data Center for Water Resource Management based in Vienna. So this is a big center with a lot of computers, a lot of computation power. And lately, the EODC also became a federated partner with WEkEO, where is providing access to the long-term archive for Sentinel-1 and Sentinel-2. And we know WEkEO, we heard about Andrea, It is the European, one of the European Copernicus dioceses. And as I said, I'm going to focus on Koala, which is in all this big data family. It's a small project that looked at how to capitalize on the Sentinel-2 data to provide services for agriculture. So Koala, because Koala was mostly implemented in Australia, and we work with the partners over there to provide services. So the classic products for land monitoring, this has already been introduced this morning. So there is a land monitoring service where we have already regularly produced products for land cover mapping, for biogeophysical parameters retrieval, some reference data, the satellite stuff. And you can find in the portal there things that, so products that look at vegetation, so forest, grassland, agricultural land, and these cover various topics, and you find data, different spatial resolutions. So this is the example for the leaf area index, going from 10 meters with the daily temporal resolution. This is also interpolated and smoothed to larger scale studies. So if you're looking for data sets that are regularly processed and present and cover large scale areas, this is probably one of the best place to go. And what is then the difference between what we do and what is produced there? Well, I mean, we made a step further. So we take the leaf area index, and this is used in evapotranspiration modeling, using algorithms that can run autonomously without compromising on the quality of the data. And in the next 5 to 10 minutes, I'm going to tell you a bit more about this. So the products we developed, we mainly look at the fertilization, so the use of chemical and organic fertilizers in agriculture. This is one a big pillar. For example, if you have an agricultural plot, field, or paddock, you want to manage the variability within this paddock according to the natural and actual variability that you have there. So you can use satellite observations to study this variability, and then you distribute the amount of fertilizer based on this variability. This is in precision agriculture called management zone map and variable rate nitrogen fertilization. So we do provide these maps so that farmers can plug into our services, obtain this map into their data management system, and perform such an application, of course, to save on fertilizer application, to reduce the impact on the environment due to over-fertilization, and in general, to be more efficient. The other big category of service, I'm moving my mouse so you can see, so the irrigation services. So lately, across Europe, across the world as well, water has become more and more scarce. And there is more attention to how much water we use in the industrial, in the domestic, but also in the agricultural domain. And here, satellite can help to, for example, understand how much water plants are using. I'm talking about the crop evapotranspiration. And if you know how much water the plants are using, you know as a farmer how much water you have to integrate with irrigation, with providing water to the plants. If we move a step further, so we go into what we call integrated water management services. Now, we are not talking about an individual farmer doing the management of a crop or a field, but we are talking about many fields together, where we want to know, for example, how many farmers are irrigating the crops, what type of crops we have, what is the water that is used in that area. And these services are more designed for water managers, for policymakers, for people who have to manage large extent water resources. So those are the services, and those are based on what we call core products. So crop evapotranspiration, water requirements, soil in the canopy water status, irrigated area maps, and so on. I'm not going throughout the list, mostly based on Sentinel-2 data. So that's the main satellite that we use. How is the system organized, and how are we connecting and delivering products to the farmers. Where the system is running in a cloud, so it's a Docker, classic Docker container with an orchestrator where you have different models that do different stuff. So we have the send to core, which is doing the atmospheric connection. This block is going to be removed because atmospherically corrected data are now already available on most of the Copernicus apps. We do leaf area index, we do albedo, we do fraction of vegetation cover using biophysical parameters retrievals models. And again, here we use open source algorithms. The send2core is from ESA. The biophysical is also provided in SNAP. So those are the algorithms we use. So this is transparent and clear. And from this algorithm, we apply additional methods, for example, to get evapotranspiration, to get maps of irrigated areas, to get management zone maps. And those are more proprietary algorithms that are developed by the different partners of the project. One component we have is also the forecast. So we want to look forward in time. So we use climatic models to have a short-term forecast on what is going to be, for example, the precipitation. That's one of the natural water input that we get from crops. So those are some of the data we use. So EO data, weather data, data at the ground, sensors, and then of course the district geometries, so the parcel geometries. Through API, we connect. We can allow connections to software such as Quantum GIS, or to specialists. So for example, this Yield Prophet is a company based in Australia that provides advisory services to farmers for yield estimation, and they can connect to our cloud-based infrastructure to obtain, for example, yield estimation and compare it to their data before they can stream it to the very end user, which in our case are farmers. We are looking at the parcel, irrigation infrastructure, or policymakers at larger scale. So this is a bit how we work. So let's go deeper into one specific product, which I believe is of interest for the audience. So it's the management zone map. It's one of the classics of precision agriculture. You have a set of data, you have a predefined process, you apply this process on demand, and you get your map of variability in the field that shows how a raster is transformed into a vector. This vector goes into the tractor and drives the application of fertilizer. Let's say now that you're a farmer and you have some experience and you want to use this experience to guide certain segmentation properties and how the satellite data are transformed into parcels, into uniform segments. So through the system, you can input this information and get a modification of the original map into something that fits best your requirements, your needs. So in this case, what we have modified is the minimum area of segments for the application. This is something that through the Koala API, you can trigger, and then you get something that fits best your requirements. This is just a definition. What this is a map that shows the spatial variability so that you can manage the fertilizer, but also the seeding and the harvesting in a selective way based on the variability you have in the field. So now to get this management zone map, it's a complex process. So we gather Sentinel-2 data atmospherically corrected. We transform them into biophysical parameters. We drop the data that are affected by cloud so that we only obtain or gather together the one that are really clean and effective. And also this process of filtering which data we take and which we drop, it's user-driven. Once we have the time series, we can then reconstruct, perform a gap filling so that we have a continuous representation on a daily scale of the plant growth. We look at the phenology of this specific field, and we do this pixel by pixel so that we have the start and the end. And after that, we look at evapotranspiration. So we calculate the water balance pixel by pixel within the start and the end of the season to calculate the total transpiration. So if you have this total transpiration, you will know the potential of growth of that specific pixel, and this is then transformed into a raster data, and for practical application is segmented into a vector data used in the machinery. So the process involved are happening with different triggering modes. So the atmospheric correction, as I say, this is today, it's a common thing. It's done as the Sentinel-2 data are collected. The retrieval of leaf area index is done also regularly, the cloud masking also regularly. Then we get the data. This is an on-the-fly process when a farmer is triggering the request. The data smoothing is also done on the fly, the phenology, the transpiration, and then the image segmentation. Of course, this has all to happen in a few seconds. To get such a process, you probably need less than a minute to obtain your map. How do we actually deliver the data? As I say, this is through an application programming interface. So there is a public address, web address, where you can modify the parameters. So in this particular case, I'm looking at ET, so evapotranspiration, for a certain geometry of these coordinates. This is near Vienna with this reference system, a certain buffer. The date is now. I want it for a period of 10 days. I want it as an image with a certain color map. And here we enter into the more domain-specific parameterization of this API. When you look at the ET evapotranspiration modeling, you want to know the leaf resistance, the crop height, and the wind measurement height. And those are parameters that you as a user can modify. And of course, then you need a token to get this activation. Results can be an image data or a table data that you can use to do web mapping or to serve other services such as yield estimation. Going back to the question of data and quality and validation, those are two examples of how we validate leaf area index through instruments at the ground. This has been work across the last 20 years. And evapotranspiration is validated through the use of evapotranspiration. So this is not a regular activity we offer, but has been conducted in the course of the project. And as a scientist, we do it continuously for our research and development activities. Another thing we have done was a comparison with another product available only for Australia from the 10 sites. It's a scientific network in Australia, and you can see here a scatter plot of the ET from Koala and the ET from the Tern site. And same comparison on a raster basis, where on the left-hand side you have the Tern, and on the central part you have the Koala products for the month of December. Now, the main difference is that Tern is monthly. It's a monthly aggregate, while Koala goes down to the day. So it's a product that allows you to do actual management of irrigation in the field. So it's not just historical environmental modeling products, but it is actually a service that can help users. So the current deployment, it's so some numbers to let you know that this is operational, it's running. We are currently using 14 terabytes of disk space. It runs on demand, so we don't process all the globe by default, but if there is an interest, we can activate the processing of Sentinel tiles. We work on a Sentinel-2 tile minimum unit, and currently we are receiving about 5,000 API requests per day. And you see how this is actually also seasonally varying. Services are mostly active in Australia, and you see that this starts in November with the start of the growing season and ends in May. This is the most active period. Also, the response time, just to give you an idea, this is for evapotranspiration. So if you request 15 days of evapotranspiration, you will probably wait 1 second for the response. Some of screenshots of people who are using the services. So Yield Prophet I mentioned already. So colleagues in Italy are using this to provide data to farmers there. Colleagues in Spain are using the API to produce dedicated consultancy services to farmers in Spain. schedule it also in Australia. And we also developed a plugin so that everybody can download the products from Koala and visualize it in the QGIS plugin. Some final remarks. Why is this so special? Because we do produce products that normally do not exist, and we do it in an automated way to reduce the costs. So there is no human intervention. The computers are producing this, but at the same time, our big effort was to maintain quality and accuracy as the classic human control processes that were taking place 15, 20 years ago. So this means that we are more efficient, it is still accurate, we can scale, we can customize, and as a result, this can save cost and becoming more affordable for farmers wanting to use agricultural data. Where are we going? So the project ended in 2023, last summer. We have next 3 years, which will be a sort of transition period, the legacy construction, and we have ambition to continue working, expanding from Australia and Europe, and providing services for testing to others who are interested. And therefore, if you think that this might be interesting for you, you can go on the Koala website where you find the contacts, also a test token that can be used, for example, to trigger the services and obtain some more products. And that's all from my side. I thank you for the attention and happy to take questions.
Thank you very much, Francesco. Indeed, we have a bunch of questions for you. Actually, the first one is something that I think it was for David before, but maybe you are actually more directed to your field. Did you encounter that data made available by WEkEO to monitor, for example, soils and crops? Did it have enough resolution? Or yeah, what was your experience with that?
Depends. Yeah, depends on the scale. So if you're looking at Australian parcel size of several hundreds of hectares, 100 hectares, for example, the spatial resolution of Sentinel-2 data is largely enough. If you're looking at very fragmented parcels of an hectare or less, then probably you want to have a higher spatial resolution. In general, I would say that for what farmers can manage, so the variability that they can actually measure and manage, Sentinel-2 data is very, very good, it's excellent, and having higher resolution will probably not result in a better management at the ground because machines and farmers do not have the capacity to manage the variability, let's say, at the meter spatial scale. This would not be sufficient.
Okay, I see. So the second one, are agricultural field boundaries available freely through WEkEO? And if not, how did you obtain them?
Well, I mean, we don't actually store and obtain data from farmers. There is an API request. So farmer, or let's say intermediary company that support farmers can stream to us the coordinates of the fields, the boundary, the JSON geometry, and then we do the processing on a cut from the Sentinel data on that geometry. So we do not collect or store data that are on the parcel boundary. However, if I might go beyond the question, in Europe, there is the Ajax system, which is the system used by farmers for reporting to the common agricultural policies, and those are data available, and you can find them from now more and more countries in Europe.
Okay. This question was also, I think, at the time for David, but you can maybe speak on your experience. Were you able to download data and just use it in a GIS program? I saw that you mentioned QGIS.
Yeah, so the data are very big. So you're looking at several terabytes of data. So normally we are not using this approach. We have not been using in the last 15, 20 years, this approach of downloading the data and getting them on our computer for processing. So this is something I think not possible anymore. But we still believe that farmers and very end users might still benefit from owning the data and having the data with themselves. So if you're talking about a single parcel of a bunch of parcels, then this is, yes, definitely possible. And you can connect to such a system via an API or a standard OGG service and download the data, or obtain the data.
Yes, tomorrow you will also be able to see more practical examples of that. We will have on our practical session someone who's going to present an example on how to download and do like quick analysis on using QGIS. So you will see that as well. And another one or two for you. Speaking of biophysical parameters, what's the progress in classifying water bodies and water courses with satellite data? What about soil moisture?
Yeah, so on the first two, I can't really answer. I mean, water is quite easy to classify. It depends, of course, on the size of these water courses. Regarding soil moisture, we do it with Sentinel-2 data, and we look at the combined moisture, water moisture of the canopy plus the soil and the first layer of the soil part. And we use the shortwave infrared combined with the near infrared through an open model, which is called Optram. It's a published model, so Optram, and this gives you a very good combination of canopy plus soil moisture. In our analysis and validation was very, very good.
Okay. Okay, one last one for you. We certainly have many questions. Thank you all for your questions. We will try to answer them and make them available to you. So are agricultural field boundaries available? Oh no, so sorry, this one we already did. Maybe this one. Do you know of any products based on remote sensing to track mowing and grazing activities?
We do have a project that would have been an alternative thing to present, which is called Saatgras in Austria. And this is within an European network of scientists, MOD6 called, that is looking at grazing and mowing events. And there will be more presentations coming up in the next, more papers also coming up in the next months. So stay tuned and look at our work, but also the general scientific literature on that.
How would people be able to find you? Would it be through Koala or, well, I mean, Koala is now finished, right? As I understood.
I think you can Google my name and my university, and you should be able to find me there.
Okay. Okay. Great. And maybe, okay, one last one. What are the minimal dimensions in square meters of a farming zone to be recognized by satellite data to be useful in Koala specifically? Can Koala be used for any farm in Austria?
Yeah, we look at fields of an hectare. So we'd say within an hectare, I think it makes sense to have some data. So if you're looking at irrigation, 1 hectare is good. If you are looking at variable rate application, you'll probably say more. I mean, it's difficult to manage the variability with parcels less than an hectare. In general, I would say we are on a 3 hectare scale. So farmers in Austria have a 3 hectare parcel. So that's quite applicable also to our local context here.
Okay, great. Thank you very much, Francesco.
Thank you very much.
It was really nice.